Do you struggle to decide how to use some collections and which one will be most effective in every situation? You no longer have to struggle. In this video, I will show you the primary aspects of each of the core C# collections and clear guidance on when to use each of them. We will focus only on these 6 collections: array, list, dictionary, stack, queue, and hash set, because they form the core of the language design. Other collections help you overcome specific difficulties. Immutable collections, for example, will support your immutable designs. Concurrent collections will help you write high-throughput code. They will almost certainly outperform any custom solution you might come up with. Other, more specialized collections come into play when solving advanced and complex scenarios. Each of these specialized collections would require an entire video to explain, so we will leave them aside. We won't talk about immutable and concurrent collections here either. Understanding collections starts from understanding these core ones. Let's begin with the array, the simplest and most fundamental data structure in any programming language. It is just a contiguous sequence of items in memory. Notably, in C#, arrays are zeroed out upon creation. An array of integers would be all zeros, but an array of strings would be all nulls. That is probably not your intention. You would need to initialize all the objects in the array before using them. That is pretty much all you have with the array. You can read or set the elements, and that is it. There is no such thing as adding a new element to an array. You would need to resize the array, copy the old content, and set the new entry. For performance reasons, it is common to enlarge an array in larger steps. For example, you could track the count of elements that are effectively populated. The remaining elements are unpopulated. Now we can think of how to add a new element. If there is still room left in the array, then just squeeze one more item in. Otherwise, resize the array, for example, by doubling its capacity. Don't forget to copy all preceding content into the new array. Let me reorder these operations. The first step is to ensure that there is additional space in the array. The second step is to insert the new element. This is an efficient protocol for adding items to a data structure backed by an array. The list class is applying a similar protocol in its add operation. Populating the list will be roughly twice as costly as populating an array of the same size. This will pay off quickly because the list will efficiently do what the array cannot: add new items. It also supports removing an item at the expense of copying subsequent items to fill the freed position. This tells you how to choose between an array and a list. If you need to add or remove items dynamically, then the list is a natural choice. If you don't need that, then you use the array. Let me start drawing a table with collection capabilities. I plan to fill these for each collection in this video. We recognize the need to add a new item, the need to remove an item, the ability to seek an item with a given value, and to operate over all elements in order. I will also add sorting. You will often need to perform such a heavy operation on the entire data structure, so let's see that one too. The array does not support adding or removing, but it does support efficient seek by the index or linear search in time proportional to the array size. It also supports iteration as well as the most performant in-place sorting you can get. The list does all that with a bit of an overhead. Additionally, note that both arrays and lists support binary search, provided that you have sorted them in ascending order first. The list also supports operations that are not available on arrays. I will distinguish adding and removing at distinct positions in the list. The reason is that the list is super efficient when adding or removing the last item, but not so at any other position. I have heard people say numerous times they use a list as a queue. This table tells why that is wrong. Here and there someone confesses they learned the lesson the hard way. A proper queue collection supports efficient addition at the end and efficient removal from the head. That is a novelty compared to the list. The other operations are irrelevant. You will hardly ever want to search the queue or to iterate it. Sorting is out of the question. The primary role of the queue is to retain the order of items. In all fairness, though, you might use the list as a stack. The stack does what the list does best, adds or removes one element at a time from the last position. The difference is in the naming, as the stack uses the names push and pop for these operations. I will dismiss other operations on the same grounds as with the queue. They just don't make sense with stacks. You will use queues and stacks in specialized algorithms. Queues are a regular tool for scheduling algorithms that require processing items in the order of their arrival. It is progressively harder to find use cases for queues in regular business applications. They already belong primarily to library code. Stacks are similar. They are a rare beast nowadays. One notable example of using a stack in a common application is to implement the undo-redo functionality. Imagine having an interface for a command. A command would be anything that happens in your application. It supports executing and undoing its work. Then comes the execution engine, which manages commands issued within the application. Executing is easy, but how do we go about undoing and redoing the past commands? That is where we find stacks. The undo stack would remember the commands from the most recent ones. Push every new command to the top of the undo stack. When the user requests an undo, try to pop the latest command off the undo stack and undo that specific command. How about a redo request? That requires another stack. Then begins the dance between undo and redo. Undoing a command pushes that command to the redo stack. Redoing means to try to pop the latest undone command and execute it again, pushing it back onto the undo stack. If the redo stack is empty, try repeating the latest user's command as if the user had sent it again. Also, don't forget to reset the redo stack when a fresh command arrives. This is the general-purpose execution engine you can embed into any UI application. Its operation is based on two stacks. That completes the story of fundamental linear data structures. Before we move on to dictionaries and hash sets, let me remind you that this channel is free thanks to the people who support it on Patreon. If you enjoyed learning from this video, then please consider becoming a patron. As a patron, you get access to the source code from all the videos on my channel, as well as to other goodies not available on YouTube. You can find the link in the description. Now back to the table of collection abilities. Dictionary and hash set remain. They cover the remaining two major areas in programming, mapping and working with sets. I will give you an interesting perspective on dictionaries. Where an array uses an integer index to provide access to an item, the dictionary takes any equatable object. Indexing into a dictionary is somewhat slower than direct access into an array, but it opens a whole range of new capabilities. Use a dictionary to create a map from the set of keys into the set of values. And then come the sets. A dictionary wouldn't allow two instances of the same key. Setting the same key again would overwrite the previous value. That makes its collection of keys a proper mathematical set, the one with no duplicates. Some programming languages, such as Go, use maps to simulate sets. Just put nothing as the value and then check for the presence of the key. .NET has always had a proper definition of a set, where deduplication is supported by hashing. Hash sets support the entire set algebra, from adding an element and testing presence, to efficient mutation using common set operations, union, intersection, and set difference. You will use a hash set in every situation where you need set algebra. Let's fill the rest of the table now. Both dictionaries and hash sets support fairly fast access, retrieval, and removal. You can also iterate their content. However, since both structures represent sets, there is no such thing as sorting them. Keep this table in mind when selecting a basic collection the next time, and combine these simple collections into more complex ones when you need them.